We use Laplace transforms for solving linear ordinary differential equations and related initial value problems. And also we use them to solve a coupled set of ordinary differential equations. So let me just write. And it becomes very easy to solve linear and coupled linear ordinary differential equations with Laplace transforms because this is a transformation which converts differential equation into algebraic equation, and you know that algebraic equations are very easier to solve. So let me just write. So it makes created initial value problems. Initial, so there are two kind of problems. One are initial value problems, others are boundary value problems. In initial value problems, some initial condition will be given. So like some process is starting, so at time t is equal to 0, initial conditions will be given. And in boundary value problems, so boundary value problems are in space. So let's say there is some structure. So at its boundary, some boundary conditions will be given that structure is fixed at a particular point, and at other point, let's say it is fixed in some another direction or rotation is fixed. So those are known as boundary conditions. Starting point of the phenomenon. Okay, so it makes solving linear ordinary differential equations and related initial value problems as well as system of makes solving them easier. Okay, so system of ordinary differential equations means you have more than two ordinary differential equations, and those are coupled. You can't solve them independently. So if you want to solve one equation, then the equation of the variable in one equation is also in other equation. So you have to solve those equations simultaneously. You cannot solve it. Systems also, the Laplace transforms make solving ordinary differential equations very easier. So let me just write how do we, what is the process of solving initial value problems using Laplace transforms. So firstly, let's say we have some IVP or initial value problem. This initial value ordinary differential equation, we have here ordinary differential equation, and it is linear. Of course, we are going to solve only linear ordinary differential equations. For nonlinear ordinary differential equations, we have numerical methods, but this is not a numerical method. We have initial value problem, linear ODE. So using Laplace transforms, so firstly what we will do is we will apply Laplace transform. And what we will do, we will solve this algebraic problem. Solve, Solving algebraic equation is very easy. There are many methods, right? So like goes forward elimination, backward elimination, these kind of methods you would have studied for solving algebraic algebraic problems. So uh, after solving algebraic problem, we will get the solution. Basically, we will have the solution of our initial value problem. Okay, so the key step is here that we are converting our differential equation into algebraic equation, and then it is very easy to solve algebraic equations. Let's see what is the form of Laplace transform. lecture is going to be very basic, then we will advance as we go ahead. So Laplace transforms are denoted by this capital F. So capital letters will be used to denote Laplace transforms. So capital F, S is the new variable, okay, and it is also denoted by capital L, and we are going to do Laplace transform of this function. So this is the original function. We are going to do Laplace transform of this function, which will be denoted by capital F. So if function will be denoted by small f, and its Laplace transform will be denoted by capital letter. So function will be denoted by small letter, and its Laplace transform will be denoted by capital letter. So finally we have, so this is Laplace transform. Okay. So we have our function, and we are transforming it by multiplying with this. This is kernel function. We are multiplying it with some kernel function, integrating it in time space. So now we will have our function in this S space. So we have transformed our function from time space to a new variable, S space. So this will be known as small letter, will be denoted by small letter, and this its Laplace transform will be denoted by capital letter. In a generalized way, so generalized definition I'm writing here. This is some transform, integral transform, which is multiplied by this kernel function. So this is a generalized definition of an integral transform. Integral transform means you are transforming a function from one variable to another variable using integration. Okay. So function was in time variable. Now I'm transforming this function into S variable using some integration, and a kernel function and multiplying it with a kernel function. So kernel function will be a function of both the initial variable and the final variable in which we are converting the function. So this is a function of both S and T. Let me write. So this is an integral transform. Here we have kernel function is e raised to power minus st in case of Laplace transform. Okay. So we can say that Laplace transform is an integral transform. Changes a function in one space. Here we have time space. Function in another space to a function. Here we have S variable S. Another spaces we just call it as S space. Okay. by a process of integration. Involving kernel. Basic idea of what is Laplace transform and how. So it is a type of integral transform which is transforming a function in time space to some another space. Start with very simple example of Laplace transform. So let's say a very simple example. So let's say we have f of t as only t. It's a very linear function, simple function, and where time is greater than equal to 0, of course. And then we want to find out its Laplace transform f capital F of s. Okay. So how will you find it? Tell me. So capital F of s, what was the definition? We just use the definition. So it was 0 to infinity. So whenever we have infinite limits, we call them as improper integrals. So improper integrals, you can also write it like this. By definition, it is limit capital T approaches to infinity, e raised to power minus st f of t dt. Okay. So we, because infinity is something, so let's say you have 1 by f of t has 1 by t. If you integrate, if you're getting 1 by t. So writing this is a good thing because you may have sometime infinity by infinity. After solving this, you may get infinity by infinity, and then you may need to apply L'Hopital rule. You would have studied L'Hopital rule. So writing this is a good practice. Otherwise, if you directly have infinity here, you will be confused. Anyway, so this is the definition of this Laplace transform. We will write limit t approaches to infinity 0 to 2 integral. Whenever we have limits as infinity, we call them as improper integrals. Anyway, so let's solve this. Solve and tell me the answer. Can you solve this? You only have to solve this integral lying in this square bracket. Yeah. Please solve this and tell me the answer. Or let's take a more simple problem. Let's take this to be 1. Okay. We don't want to apply product rule of integration. So let's take this to be 1. Okay. Or f of t is 1, is a constant function. Yeah. So now tell what should be the integration of this function? Yes. Hope you remember this much of integration. Yes, Ashwini. power minus st divided by s and minus of that, and if you do 0 to t, and finally you will get minus of e raised power minus s capital T divided by s, and then minus minus will be plus. Okay, and e raised power 0 divided by s. Okay. So e raised power 0 will be 1, and if you put the limit here, e raised power minus infinity will be 0. So this will be 0 and this will be 1 by s. Transform of 1 is 1 by s, right? Calculate another example. Calculate, let's say our function is f of t is e raised power at, and we want to find Laplace transform of this function. Yes, please do it. E raised power minus st dt, and then again I'm not using this process that limit t approaches to infinity 0 to t. I'm just writing this as 0 to infinity, and it means the same. So whenever you are stuck, you just go back and write it as limit t approaches to infinity 0 to t. Please tell me what should be the answer of this limit. So if you solve this, it's very easy. So e raised power, you can write it as a minus s, right? Integrate, you will get a minus s divided by a minus s, right? And you can also, so it is 0 to infinity, and we are assuming that s is greater than a. So finally you can write it as s minus a over minus here s minus a, and this is going to 0 to infinity. Yeah, I didn't go sudden. So मेरा पे here from this step to this step, we have assumed that s is greater than a. Okay, only when you can write or not this step to this step. We have assumed that s is greater than a, so that only then you can write it like this, because s minus a now is a positive quantity. And now if you put the limits, so e also. So now if you put the limit, so this will be minus infinity, because s minus a is a positive quantity, t is infinity. E raised power minus infinity will be 0, and then minus of e raised power 0, that will be 1. So finally you will get 1 over s minus a, right? So fine. So we say that L of e raised power at is s minus a. So now we will define some property of Laplace transform. So Laplace transform have a linear property, that they are linear in nature. So what do we mean by that? So let me just write it here. Property. So let's say you want to find Laplace transform of a function f of t which is multiplied by constant a plus a function g of t which is multiplied by function b. Right? So this is the total function. Okay? Arity means firstly what you can do, you can find Laplace transform of f of t and then you can multiply it by a plus you can find Laplace transform of g of t and then you can multiply it with b. So these two will be same. So this is the linearity property of Laplace transforms. So for example, let's say we want to find out uh, Laplace transform of example. Say we want to find out Laplace transform of cos hyperbolic at hyperbolic at. So what is the form of cos hyperbolic function? So it is e raised power at plus e raised power minus at divided by 2. So this will be Laplace transform of e raised power at minus plus e raised power minus at divided by 2. Okay. So then with using the linearity property, we can just write that it is 1 by 2 Laplace transform of e raised power at plus 1 by 2 Laplace transform of e raised power minus at. So we have just found out what is the Laplace transform of at. So it is 1 over s minus a. So finally you will get s minus a. And Laplace transform of e raised power minus at will be nothing but 1 over s plus a. You can just try to find out and you will get 1 over s plus a. Okay. Because you have to replace a with minus a here. You can try to find out. You just put in this formula here e raised power minus at and then you will get 1 over s plus a. So finally, if you solve this, so you will get 1 by 2 we can take common and we have s minus a and s plus a here. Plus s minus a. So what you will get? So you will get 2s and 2 and 1 by 2 will get cancelled. So we'll get s over s square minus a square. Okay. So this is the Laplace transform of cos hyperbolic a, which we can easily find out using the linearity property of Laplace transform. Now, similarly, one more example I would like to take. So let's say we want to find Laplace transform of cos of omega t. Okay. So if you're trying to find out, so can you try to find it out?
Why should I what are we ignoring?
So it will be e raised power, 0 to infinity, e raised power minus st cos omega t dt. Right? Can you try to solve this? So here you will have to apply product rule. So in product rule, in product rule of integration, you have to choose first function and second function, which is chosen using this rule. So here we have an inverse function, inverse trigonometric function, then logarithm function, algebraic function, trigonometric function, exponential. So we will choose exponential function as the second function and this is the first function because exponential function is coming at the end. Differentiate the first function and we integrate the second function. So if you solve this, so let me just do it for you. So cos omega t will remain as it is and it will be e power minus st integration 0 to infinity. I think this will be reverse. Just wait. Yeah. Yeah, we differentiate the first function and we integrate the second function. Integration of cos omega t will be minus of omega and omega t and you integrate e raised power minus st dt. Will be this will have limit 0 to infinity, and this will also have limit 0 to infinity, and this will have. So then you have cos omega t e raised power minus st will be e raised power minus st divided by s, and then minus s, and then you go 0. This whole thing will go from 0 to infinity, and then plus omega, then you have 0 to infinity, 30, and then here you have e raised power minus st divided by minus s again, and then you have dt again. So you have to do it one more time. So let's call it as integral I. Put infinity, so you will get 0. Here it is minus infinity. Finally, you will get cos omega t divided by s, and then here you have minus, and you get omega 0 to infinity. And then here you have to apply this integration by parts again for this integral. So again, you will choose algebraic function as the second function and trigonometric function as the first function. Okay, so again, if you will do it, you will get this same term again here in the integral, and you shift that term to the left hand side and solve it. So finally, you will get this integral equal to s over s square plus omega square. So just wait a minute. This cos omega t should also go. So yeah, so if you put infinity here at the place of time, so this will be some, this is bound between -1 to 1, and this will be e raised power minus infinity, so that will be 0. And then you have minus minus plus, put 0 here, so cos 0 is 1, and this is also 1. So you will get 1 by s here, okay. Anyway, so finally you will get s over s square plus omega square. And then finally you will get this term. So what we can conclude is, so Laplace transform of cos omega t will be s over s square plus omega square. You just have to solve this integral, okay. We will get omega square from here, because if you integrate it, I mean, if you apply integration by part once more, so you will have the term which is, if you differentiate sine omega t, you will get omega cos omega t. So that omega will be multiplied with this term, so we get omega square. Okay, so you will get omega square from here. Anyway, so let me just clearly Laplace transform of sine omega t will be omega over s square plus omega square. And then you can find Laplace transform of n number of functions. It's not limited. So you just have to put the function here in this integral. Least you can substitute different functions, and you can get the Laplace transform of all the functions in the world. But sometimes you might not be able to calculate the integral with your own hands, because this function may be highly non-linear. So there are other properties of Laplace transform. So let me just write it for you. So firstly, we will just write some basic Laplace transforms. Mm. I'm just writing. So here we have, let's say, f of t, and its Laplace transform L of f of t. Okay. So let's say we have first function, which is 1. So we have seen that Laplace transform is 1 over s. And then we have, let's say, function t. So its Laplace transform will be 1 over s square. And then we have the third t square. So its Laplace transform will be 2 factorial divided by s cube. And then we have the fourth function, which is t raised to power n. And our n is an, let's say, natural number. So it is going from 0, 1, 2, 3, and so on. Then our Laplace transform will be n factorial divided by s to the power n plus 1. And you can find this table anywhere. It's available in all kind of books. I'm just writing it for the completeness. So, and then let's say we have t raised to power a. Now a is a positive number, positive real number. Our Laplace transform will be gamma function, gamma of a plus 1 divided by s to the power a plus 1. And you would have studied gamma function, right? So I think as far as I remember, so it is uh, gamma function is at least, remember the definition of gamma function? Yes, I think gamma of x is, yeah, can someone tell me? Say, right, x plus 1. Gamma function of x plus 1 is nothing but 0 to infinity e raised power minus xt f of t dt. No, I think let me just see. Right. So it is t raised to power x and then e raised to power minus t dt. So this is the gamma function. So here when you have x plus 1, here you have x, one less uh, number compared to x. Okay. Integration is respect to t. So you will get a function in terms of x. Okay. Because you are integrating with respect to t, so t will disappear. So yeah, so this is the gamma of a plus 1. So gamma of a plus 1 is 0 to infinity t raised to power a e raised to power minus t dt. So this is the Laplace transform of t raised to power a. And then let me just write for few more functions. And then you have Laplace transform of e raised to power at. So that will be 1 over s minus a. We have just found out. And then you have Laplace transform of cos omega t. That will be s over s square plus omega square that we have found out. Then we have Laplace transform of sin omega t. This will be omega over s square plus omega square. And then we have Laplace transform of cos hyperbolic at. That also we have found out. So that is nothing but s over s square plus a square. Then we have Laplace transform of sin hyperbolic at. So that will be, it was plus or minus? Yeah, so it is minus s over s square minus a square. So and then you have sine hyperbolic at. So here you have a over s square minus a square. Okay. And then we have, let's say, e raised power at cos omega t. So we will have s minus a over s minus a to the whole square plus omega square. Then we have, let's say, e raised power at sine omega t. So its Laplace transform will be omega over s minus a to the whole square and omega square. And for all of them, you can calculate Laplace transform manually as well. Okay. The process that we have followed here. Try to get the Laplace transform of this cos omega t. Okay. Half of the steps I have done, but later on you will have to apply more steps and get to the final answer. Yeah, I think we have the Laplace transform of all these basic functions. Now we will using the Laplace transform of these basic functions and the property of Laplace transforms. We will calculate the Laplace transform of some complex functions. So let's see what are the properties of this Laplace transforms. So first, few more properties. Again, I'm coming to the properties. When you multiply any Laplace transform with e raised power at, so let's say you know that Laplace transform of f of t is capital F of s. Then if you multiply that function with e raised power at, then the Laplace transform becomes f of s minus a. This is known as S shifting property. So you have shifted your S from S to S minus A. And this is visible here also. So you know that cos omega t has a Laplace transform of S over S square plus omega square. But now you are multiplying it with AT. So you just have to replace S with S minus A. So here we have S minus A, and then here also we have S minus A. Similarly, you have sine hyperbolic AT. This is the Laplace transform, and if you multiply it with e raised power AT, then you just replace S with S minus A. Okay, you get the Laplace transform. So this is the first property that we have. This is known as S shifting property. And then we can also take inverse. So you have this um, so inverse of Laplace. So like you know that we have differentials and then its inverse kind of inverses integrals. Okay, so similarly we have inverse of Laplace transform as well. So if you take inverse of f of s minus a, so you will get e raised power at f of t. And the similar thing is true for these functions. So if you take inverse of 1 minus 1 by s, you will get 1. Inverse of 1 by Laplace inverse of uh, inverse Laplace transform of 1 over s square will be t. Inverse Laplace transform of 2 factorial over s cube will be t square. Inverse Laplace transform of n factorial over s raised to power n plus 1 will be t raised to power n. Okay. So then, so also one more thing I would like to tell you here. This is known as a shifting property. Then we have something known as existence of, or what kind of functions exist the Laplace transforms exist. So, function need not to be continuous, but it should not be abruptly. Okay, what is gamma function? So gamma function I have told you. This is the definition of gamma function. Let's say you want to calculate gamma function of 3, for example. Say you want to calculate gamma of 3. So gamma of 3. So here x will be 2, right? You just put x equal to 2 here. So it will be 0 to infinity. T square is power minus t dt. So you just solve this integral. So you will get gamma of 3. So it's a mathematical definition. So this function because appears many times in mathematics, so we call it as gamma function. And you can solve this integral either with your own hands or you can use numerical integration solving it. You can use computer also get this value. And for integrals, as we have said, for integral, I think its value will be 2 factorial. Yeah. Can you just confirm? Can you just use internet to find out the integral because we'll use numerical integration. So I think its answer will be 2 because for integrals, if you are calculating gamma of 3, that will be 2 for integers. Okay. For integers or yeah, natural numbers. For natural numbers, gamma function is simply factorial. I'm not sure about it. You just check it. Okay. But I'm sure that it will be factorial. It may be 3 factorial or 2 factorial, and you need to confirm it. Okay. So existence of Laplace transforms. So Laplace transforms exist for discontinuous functions also, but those functions should not be abruptly discontinuous. So wherever they are discontinuous, their value should be defined at those ends. So we call those functions as piecewise continuous functions. They are discontinuous at some points, but then they start being continuous again. Then they become discontinuous at some point. Then they start being continuous up again. And the point where they are discontinuous, they have some value. So those are known as piecewise continuous functions. So Laplace transforms exist for piecewise continuous functions because integral exists for piecewise continuous functions. So for piecewise continuous function, you can always calculate area under the curve. Those are known as definite integrals. So they exist for piecewise continuous functions. Let's say f of t where time is obviously always greater than equal to 0. And then this function should not be unbounded. Okay, unbounded means going to infinity. It should be bounded because otherwise the integral will also become infinity, right? Although in time we are going from 0 to infinity, but we are getting finite value of the integral. It means our function is not going to infinity. Even we are going from 0 to infinity, we have finite value of integral. Okay. So it should be some bounded function. I mean, just writing it bounded function, this is a very layman term, but for exact mathematical description of what kind of boundedness it should follow, you can refer crazy. So it's written in terms of some constraint, mathematical constraint. But I'm not writing it here because it's not required as of now. But you can always refer to the book and understand what kind of exact boundedness it should follow. Anyway, so let me go ahead. Now we are going to, okay, one more property is there. Mm, Just wait a minute. Anyway, so let's do Laplace transform of derivatives and integrals. We know that Laplace transform of f of t is capital F of s. Then what is the Laplace transform of f prime t? Okay, so that will be actually s times f of s minus. So you please notice that this is capital F of s, which is the Laplace transform of f of t, and this is small f of s, means it is function evaluated at t is equal to 0. Function f of t at t is equal to 0. And we can very easily prove it because let's see, f prime t will be e raised power minus st f prime t dt. in 0 to infinity. So um, again again we use L'Hopital rule. So firstly, sorry, again we use product rule of integral. So we will assign this as a first function, yeah, and this as the second function, and then apply the integral. So it will be first function, then integral of second function dt minus differentiation of e raised power minus st. So this let me just write here d by dt. Everybody knows how to apply an integral of f prime t dt, and then integral of this whole thing, right? 0 to infinity, and then here limits. Do not put 0 to infinity here. It is wrong. Okay, this should not be done. This is wrong because it goes in the whole limit for the first term. So is in the whole term, not particularly for that integral. So if you do that, so you'll get e raised power minus st, and integral of uh, f prime t dt will be f of t, right? Because integral of differentiation of a function is the function itself. So and then you are going from 0 to infinity, and then if you differentiate e raised power minus st with respect to time, so you'll get minus s time e raised power minus st. So and minus minus will be plus. So finally you will get s will come out. So you'll get e raised power minus st, and integral of f prime t dt will be f of t, and then you have dt, right? So we started with this integral here. Let's call it as I. So or L of f prime t, right? This is L of f prime t. So finally, I just put the limit. So if you put infinity here, so we get uh, e raised power minus infinity, which is 0, right? And then you get minus of f of 0 and e raised power 0, which is 1. So finally, this term will be minus of f of 0 plus s times, and so this is going from 0. So this is nothing but Laplace transform of function of t, right? So finally, we have got this formula. So Laplace transform of function f prime t will be s of capital F of s, or Laplace transform f of t minus f of c. That's what I have written here. Okay. So this is the first, you can say third formula here, and then let's find out the Laplace transform of f double prime t. Okay. Fourth transform of f double prime t. So that will be nothing but if we just apply this formula only. So now our here we have f double prime t. So here we will have f prime t. So we can say that is s of uh, say that Laplace transform of f prime t minus f prime of 0, right? Because it was Laplace transform of f of t. Here if we had f prime t, now we have f double prime t. So this will be Laplace transform of f prime t. And Laplace transform of f prime t is as f of s minus f of 0. Just substitute here. Square capital F of s minus s f of 0 minus f prime 0. Transform of f triple prime t as well. So fine, now let's go to the Laplace transform of integration. So generalized formula I'm writing. So Laplace transform of f uh, n times you are differentiating the functions, which is a function of time. So finally you will get s to the power n, right? And Laplace transform of f minus s to the power n minus 1 f of 0. Then you'll get s to the power n minus 2 f prime 0, and it will go minus, it will go up minus 1 of 0, function evaluated at 0. This will be the generalized form. You can just put n is equal to 2 here. So this will be s square Laplace transform of f, which is capital F of s, minus s to the power 1 f of 0, which is here, and then s to the power 0, which is 1 f prime 0, which is here. This is the generalized formula. Laplace transform of integral, if we see, so let's say we want to find Laplace transform of integral of 0 to t, we have the some function. We are just integrating our function with respect to time, and we want to find Laplace transform of that function. And this will be 1 over s f of s. You can try to derive it. Okay. Similarly, we can also say that inverse Laplace transform of 1 over s f of s will be this function 0 to t f of tau deta. Okay. So I think I would like to stop here. In the next class, we will so these all things were related to how to find Laplace transform of functions, different kind of functions, and this is your homework that you have to, in the next class, you have to complete the second step. Read this. So okay, and in the next class, we will also look at how to apply these Laplace transforms to solve ordinary differential equations, linear ordinary differential equations. Yes, somebody is asking. Yes, Shifa, you're asking something. So this is all about uh, evaluating Laplace transform of functions. And then from now onwards, we will look at application of Laplace transforms in solving ordinary differential equations. Please remember, we have already done some method of solving ordinary differential equation. I taught you how to solve homogeneous differential equation, non-homogeneous differential equation, right? So we will compare how Laplace transform makes our job easier compared to those methods. Okay. Please revise those methods as well. I think that was lecture 1, 2, 3. Stop here for today. Thank you for your attention. And please ask your friends to join the class. The attendance is really very low.